With the rise of the IoT, or Internet of Things, connected devices are becoming increasingly prevalent, including smartwatches, intelligent cars, surveillance systems, and personal assistants. And of course, smartphones. As a result, the volume of data being generated is exploding. The massive amount of data race is overwhelming. The bandwidth between disconnected devices and the data centers that process that information. The result is slower data processing, which can be a big problem in situations where we need to analyze and process data almost instantly. This virtual edge computing offers a solution. Rather than transmitting all data to a remote data center for centralized processing, edge computing processes part of these massive data volumes locally and in a centralized manner, either directly by the connected devices themselves, by or a local machine like a computer or a server. The immediate benefit is reduced latency, as data no longer need to traverse a large network to reach a distant data center. This ultimate improves servers quality. In this way, edge computing complements cloud computing. Each layer of the architecture has a specific role. IoT layer provides the human-machine interface. Connected device generate, compress, and pre-process data before sending it to the edge layer. Edge layer handles the data analysis, real-time processing, and caching. Cloud layer performs large-scale parallel data processing, such as big data or machine learning tasks. It also conducts global analysis of data from all devices and acts as a data warehouse for all connected devices. In summary, data requiring real-time responsiveness is processed locally at the edge. Less time-sensitive data is sent to the cloud for historical analysis, large-scale processing, and long-term storage. Let's see an example without autonomous vehicles. Autonomous vehicles rely on a multitude of connected devices, which generate vast amounts of data that need real-time processing. A prime example is the autopilot features and vehicle. Sensors at the front of rear detect other vehicles. A video camera above the windshield identifies lane markings, traffic lights, and pedestrians. A GPS system and the laser-based radar analyze and surroundings, including obstacles. This critical data cannot afford to be sent to a data center for processing, especially if a vehicle is in an area without no network connectivity. Thus, critical data is processed locally directly by the onboard supercomputer. All data generated by the vehicle's sensors are analyzed and processed by the board supercomputer, which is a part of the edge. Some other data, like summary, inform about the vehicle's status, is sent to an intermediate edge server. Relevant data from the edge level is then transmitted to data center where it is analyzed globally and processed. This enables the creation of predictive models to improve the vehicle's intelligence, which are then distributed back to the all vehicles. If you enjoyed this video, hit that subscribe. Edge computing is a distributed IT architecture that brings data processing, storage, and application closer to the data source, such as IoT devices or local edge servers, rather than relying solely on a centralized, distant cloud data center. This approach reduces latency, increases operational speed, lowers bandwidth cost and improves reliability for real-time application. Definition and purpose. It moves computation to the edge of the network near where data is generated. It is designed to overcome the limitations of cloud computing, such as high latency and bandwidth constraint. How it works. Data from devices, cameras, sensors is processed locally on edge nodes or gateways. Only essentials analyzed data is sent to a central cloud for long-term storage or deeper analysis. So, they are the key benefits of edge computing. Reduce latency, enable instantaneous real-time responses necessary for autonomous vehicles, industrial robotics, and AI application. Bandwidth efficiency. By processing data locally, it reduces the need to send large volumes of raw data to the cloud, saving on network costs. Improve security and privacy. Sensitive data can remain within local networks, decrease risk associated with the transmission. Reliability. Operations can continue during internet outages or connectivity issues. Common use case: industrial automation. Factories use sensor for real-time quality control and predictive maintenance. Autonomous vehicles, self-driving cars process data instantly on board rather than waiting for cloud input. Smart in retail and cities, in-store analytics and smart traffic management system. Healthcare, real-time patient monitoring and telemedicine application. So, edge versus cloud computing. While cloud computing offers vast centralized processing, edge computing provides distributed, immediately and local processing. They are often used together in a hybrid model to balance instant, localized action with long-term, deep data analysis.